Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Hi, now we're going to continue with chapter 52. We're actually now at section 523, current carrying capacities of cables. We're going to do 523 and 525 kind of together in like one process, and then 524 kind of just thrown in the end of that. I think that's probably the best way to do this. Right. So 523.1, the current including any harmonic current. Harmonic currents we discussed a few videos ago, where we talked about the potential harmonic content with non-linear loads and things like that. To be carried out by any conductor for sustained periods during normal operation shall be such that the appropriate temperature limit specified table 52.1 is not exceeded. So normal operation. So a thermoplastic cable, typically 70 degree at the conductor. Thermosetting, 90 degree at the conductor. The value of current should be selected in accordance with regulation 5232. Determined in accordance with 5233. So 5232 states, the requirement of regulation 5231 is considered to be satisfied if the current for non-sheathed and sheathed cables does not exceed the appropriate value selected from the tables of current carrying capacity given in Appendix 4 with reference to Table 4A2 subject to any necessary rating factors. So the first thing is it mentions a table. So let's go to there. We looked at this table previously in Appendix 4. I think the example we looked at was Table 45. So let's go back to that one. 45. Okay, that's page 409. This gives us the current carrying capacities for flat profile cables, the twin and earths, basically. Looking at that table, it gives us the cable size down the left and the methods of installation across and the corresponding current carrying capacities. What's table 45 is quite unique in that it's just one table. 45 is the one table, and the very, very right column is the volts drop column. If you were to change to cable type, let's say, for example, let's find the equivalent multi-core. If you went to table 4D2A, which is a multi-core 70-degree thermoplastic insulated and thermoplastic sheath cable, so very similar to twin and earth, but obviously a round sheath. The current carrying capacities are the same, fairly similar. You've got the sizes, but then you have the reference methods. In this case, we have A, B, C, and E. And in either whether the circuit is a single or three-phase circuit. But the volt drop table is not on the right. Instead, it's on the next page, 4D2B, where it has the sizes down the left and then the corresponding volt drops in millivolts per amp per meter for, whether it be a three-phase, single-phase kind of setup or a DC setup. So every cable type is here. Copper, aluminium. When you're looking for a cable type, do make sure you understand, first of all, if it's thermoplastic or thermosetting, and also look for if it's armored or non-armored, because it's quite an easy thing to miss out on, and the cables do change. But it also says here, so it says, the reference to table 4A2, but then says subject to any necessary rating factors, 523.3. So the current carrying capacities given in the tables are provided for guidance. It is recognised that there will be some tolerance in the current carrying capacities depending on the environment, the conditions, and the precise construction of the cable. Again, typically these are a guide. Manufacturers may have a slightly more accurate data sheet. So rating factors. Now these are the reference methods that we just saw. Reference method A with a thermal insulated wall. B, containment on a wall. C, clipped direct, which is the best ones. But the reference methods are, the rating factors. The rating factors are a few things to consider, but there are considerations on things within the method of installation that in some way affect the cable's current carrying capacity. This is done. Most often this is because the method of installation has resulted in a duration in the ability for the conductor to give off heat. And when we say a conductor runs at 70 degrees, what we're saying is at the cable at 70 degrees, that's the limiting temperature because the insulation will reach a limiting temperature. If we install the cable in a way that reduced the ability for the conductor to give off that heat, we're derating it. So we're going to say no, it can only carry that much instead because we don't want it to build up to that actual true temperature on the conductor due to the stress from the inability of heat to escape from the conductor under load. So a couple of things we need to consider. We need to consider ambient air temperature. So the cable's current carrying capacities in Appendix 4 are given at 30 degree as the ambient. If we were to say a cable can carry 27 amp at 30 degree ambient, if we then installed it at a constant temperature of 35 degrees, it's obviously going to be a little bit less because it's a little bit warmer. Similarly with grouping, we've got to consider if the cable's going to be grouped with others. Thermal insulation. Thermal insulation is technically, it is a heat barrier. It stops heat escaping, but it also means it stops it, leaving cables as well. So if you put in thermal insulation around the cable, you're really suffocating that. Temperature changes within the conductor. Type of protective device. We touched on this one previously. When we looked at the overcurrent protective devices, we talked about the BS3036 protective device in particular. And there was something that said we had to consider the long time it takes to operate under a fault condition, specifically overload. And there was a factor of 0.725 when we covered that. Okay, think back right now to when we talked about protection against overcurrent. Which was chapter 43, obviously, section 433. Protection against overload currents. And we mentioned this thing, and we're going to revisit this right now, but we mentioned this coordination thing. Yeah, and if you look at 433.1.1, you'll see it there. So the operating current of the protected device shall be not less than the design current, and the rated current carrying capacity of the device IN should not be less than the IZ. And then it said in the which one was it? 533.1.202. It says if it's a 3036 fuse, then compliance with the above will be achieved if we have a 0.725 factor. So, the type of protected device also needs to be a consideration for that. Also back there, in 433, underneath, there was a mention of when we're burying it in a duct, the temperature would be 20 degree. So we, again, apply a factor of 0.9. Similarly, we may consider the depth of burial and the thermal resistivity of the soil. All of these things are factors that can affect cables under load. And so we'll look at those now. Do remember, the let's see if I can. The coordination is important, and we're going to revisit this when we do a little design. But do not forget. So I can get this off on there. Do not forget this bit. Oh, camera down. There. The IB must be less than or equal to IN which must be less than or equal to IZ. Design current must be less than or equal to the protected device current, which must be less than or equal to the cable's current carrying capacity. Okay, I plan on using a whiteboard, but to be honest, it was just too much of a faff. So what I'm going to do is at the end of the video, I'll just cut and edit me doing it on paper. It's just easier because I'm a lefty. I write on a whiteboard and I just rub it off when I hold it in front of this thing. So I tried, but we'll do it on paper afterwards. But that's coordination. Don't forget the coordination. IB-IN-IZ. We're going to follow that through as we do this process. But let's look at these rating factors. The first one, CA. Okay, 523.4. The ambient temperature shall be considered to be the temperature of the surrounding medium when the non-sheath or sheath cables are under consideration are not loaded. So, if we go back to Appendix 4, and again, there's an awful lot of Appendix 4 backwards and forwards here. In fact, actually, at this point, let's cover this. Go to the beginning of Appendix 4, page 373. It gives you a list of all schedules, and the rating factors are kind of previewed there. 4B1, rating factor for ambient temperature. 4B2, rating factor for ambient ground temperature. So there's mention of the rating factors there now. But it's kind of like a mini guide here. If you actually read through it, and kind of as a little revision exercise for cable calculations, it's very useful. But let's go to section 3, page 376. It then tells you relationship of current carrying capacities to other circuit parameters. And there's a list there of some things we already now know. IZ, current carrying capacity of the cable for continuous service. IT, that we're going to value soon. That's the tabulated value of current carrying capacity. IB, the design current, we should know that one. IN, the rated current of the protected device. And I2, the effective current disconnecting the device. But then we have these C's, and this is what we're looking at right now. So C's are rating factors. They'll be applied when installation conditions differ from those which are the values of current carrying capacity are tabulated in this appendix. So CA is for ambient temperature. Yeah, oh, that's there. We'll have CC for cables buried in the ground. When we know that, that's 0.9. CD for the depth of the burial. CF, if it's a semi-enclosed fuse, would be a 3036, which is 0.725. CG for grouping, CI for thermal insulation, and CS for thermal resistivity of the soil. Okay, and then there's a little paragraph just underneath that reminds you of coordination. The rated current of the setting of the protected device IN must be not less than that of the design current, etc., etc. So it reminds you of coordination there as well. And then on the next page, it talks about overload protection, and through all of that, it talks about fusing factors, and it talks about 3036, 1.45 over 2 equals 0.725. It's just explaining it a little bit here as to why we have to consider these factors for overload protection. Do remember that overload only occurs on socket outlet circuits or motor circuits, equipment that can overload in a fault-free condition. It's not fault protection, it's overload protection. We're going to remind ourselves of that because soon I'll be saying, is our load likely to overload? Yes or no, and that will depend on if we use that factor if the protected device is a 3036. We then have a number of formulas in 5.1. There's a formula for single circuits. There's a formula for groups. Overload protection is not required. Other frequencies, etc. But before we go into that, let's look at the rest of these rating factors. So the first one we saw was table 4A1. Not table 4A1, 4B1, which was just after the very large table 4A2. So table 4B1, page 394. That's this on the slide here. Now we've mentioned all of the cable's current carrying capacities are dictated or declared at 30 degree. So when you look at that table and you see the 30 degree temperature, you'll notice that all of the rating factors are 1. If you put this into math, which is what we're going to do with rating factors, what 1 does is nothing. 1 means no effect. Yeah. If I had a 70-degree thermoplastic cable and I had it at 35 degrees, I divide the rating either IN or IB by 1.03, which actually makes it less due to the cooler temperature. However, if I had a 40 or a 45 degree, then I'd be applying a 0.87 or 0.79 factor respectively. So, this is fairly obvious. First thing is, is your cable 70-degree thermoplastic or 90-degree thermosetting or whatever? And what is the ambient temperature? And then find your factor. Fairly simple. If you're doing tabs, it's up to you, but this would be tabbed as CA. This is where your CA is from. We then have underneath another table for CA, table 4B2, but this is referring to a ground temperature. So in that case, as we knew with the CC factor, where it was 20 degrees was the norm, you'll notice that 20 is 1, and it's only if the ground temperature is different to 1 degree, 20 degrees, we apply a factor. On the next page, table 4B3, this refers to the soil's thermal resistivity, so the actual, the effectiveness of the soil. And then 4B4 is the depth of the burial. So if I was to say that you're going to bury a cable and it's buried direct to 1 meter, you would then look at this. Buried direct or in buried ducts, it's buried direct 1 meter, 0.97. Okay, so this is all about buried cables and ambient air temperatures. The another interesting one is your grouping. Now, I've already started preparing it, but I need to do a dedicated video on this subject. I'm seeing a lot of electricians who do do great looking work, and they obviously, workmanship is really, really good. But one of the things that they often will do, especially in consumer units, is that all of the neutrals will be nicely tied together, and all of the lines will be nicely tied together. So you end up with just this large brown bunch, and then going to fine little MCBs. I appreciate it's a good looking job, and I'll be honest, I did it a lot like that myself for a long time. The problem with that is if the designer hasn't considered that bunching effect, then there could be a problem with the overall current carrying capacity of the cable. I will just flag a couple of images to example this right now, just here. Yeah. I think good workmanship is great. I think you should try your best to do that, but we do need to remember that if the designer has not said that this circuit is going to be bunched, we should not then bunch the circuit to make it look nice, okay? So the grouping table 4C1, page 396. Now this table requires understanding of the reference methods. We've talked about reference methods, A, B, C, D, all of those. So when you're looking at this table, what you do is you have your items, 1, 2, 3, 4. Then arrangements of cables that are touching. So it's only if the cables are touching. Now this could be they're touching, such as here. That's fairly obvious. But it could be one cable that's actually surface clipped next to another, but then just this side, this part of the cable is touching. Because if you think about it, let's say that my fist is a cable. It's trying to give off heat or some temperature under load. And if I then to put it next to another one, and they're both trying to give off load under demand or under load. They're trying to give off heat under load. One is going to oppose the other. There's going to be a level of challenge, and so that part of the conductor is going to be restricted, and it's then going to need to be limited. That's what this is about. So we look at the reference methods. We have A to F on the far right. That's bunched in air on surface, embedded or enclosed. Then we have reference method C, single layer on a wall or floor, and then we have on tray systems. Then we have the number of circuits or multi-core cables. So if I was to install a circuit and I was to then bunch it with 2 other circuits, I would have 3. And if I had that surface clipped, 3 clipped on a wall, 0.79. Okay? But that is a consideration of the grouping factor. Now if I had them grouped through a higher ambient temperature, I'd have to apply both factors simultaneously because they are grouped, which is a deration, and they're in a higher ambient temperature at the same time, which is a deration. I multiply the factors together to create another unique factor. But, and it says this in 523.8 back in 523, the current capacity of a cable must be determined so as to be appropriate for the part of the route having the most adverse condition. So this illustration shows you a 60898 fuse board. So there's no 3036 fuse, there's no CF factor. We have a cooker circuit, we have a shower circuit. The cooker circuit is bunched with the shower circuit up from the board to under the floor upstairs. So there will be a grouping factor here applied for both cables. Let's say it's surface clip bunched, so that is 4C1 surface clipped 2 circuits. That's 0.85. There's a 0.85 factor applied to both of these cables for this 2 circuit bunching. This then gets to the cooker, that's fine. But this cable is also going to go through a higher ambient temperature in the loft. So I've got 0.85 as a bunching factor, but I've also got to consider the ambient air temperature. This is a 70 degree thermoplastic. So if I go back to table for CA, 4B1, that tells me the 70 degree thermoplastic requires a factor for 35 degrees of 0.94. So 0.94 is required for the ambient temperature in the loft for this run, and 0.85 is required for the grouping for the run. But as we've just said, if they don't coexist, then we don't have to multiply them. It's bunched, and then it's run, and then it's the ambient air temperature. So what I do is I decide which of the factors is worse. And with factors, it's always the one that's nearest 0. Because the worst factor is the one that obviously, adjusts the value most. So a factor of 0.94 is actually better than a factor of 0.85. 0.85 is going to be a larger duration from 1. So because of the 0.85 here for the bunching, applying this factor to this cable for the bunching already accommodates the requirement for the ambient temperature in the loft space. So I don't need to apply the 0.94 factor. If it was bunched in the loft with another cable, then I'd multiply them together. So we always identify when these factors are required. Another one is the CI. This is the thermal insulation. Now, when we install cables, we need to try to install them in a way that allows a thermally conductive surface to be on one side of the cable. And we're talking mostly here about plasterboard. You should always make sure that part of the cable is in contact with the plasterboard to allow, obviously, some level of thermal energy to escape the cable and leave. If you smother it with thermal insulation, it ain't going to last much longer. So if we run it through thermal insulation like that, or as you can see a little gap here, maybe this is like we've got a lot of houses now, an old layer of insulation, then we had cabling just thrown over it because, someone was very incompetent. But then another company comes and puts a new layer of insulation on top. We've got this in a lot of properties. There was an incentive 10 or so years ago for more insulation in the lofts, and a lot of loft spaces were just flooded with thermal insulation, especially in social housing. So it's a big issue that we have. Now, there's no factor for this in the appendices. This factor is actually back in 5239. So I go back to 5239, and it tells me cable and thermal insulation should preferably not be installed in a location where it's liable to be covered by thermal insulation. Where it's to be run in a space with thermal insulation is likely to be installed, it will, wherever practicable, be fixed, clipped, alright, in a position such that it will not be covered by thermal insulation. Okay. 2 paragraphs down. For a single cable that's likely to be totally surrounded by thermal insulation material over a length of 0.5 meter or more, then the current carrying capacity will be taken in the absence of more precise information as 0.5 times the current carrying capacity for the cable clipped to a surface. So it's half of the highest reference method. Okay? So if I was to have a cable and I was to say, let's go back to 4D2A. If I was to say, okay, my cable is a 2.5 and it's single phase, that's 27 amp. If I've installed it like this, that's 13.5 amp. So, you know, it's clearly a problem. It really, really affects cables. If it's a length that's a lot shorter, you know, 0.4 meters down to 50 mil, then there is this table, 52.2 in the regs book. Alright, so we've got to understand that, how to find these factors. So we've talked about CA, CI, CC, CG, CF, CS. So try to familiarize yourself with them. It just takes a little bit of revision. The common ones, though, will be CA and CG, ambient air temperature and grouping. CI is only if there is thermal, and CF is only if there is a fuse. All of CC, CS, and CD are only if it's a buried cable outdoors. So, you know, you don't have to worry about those necessarily too much. Alright, so that's a little bit of the relationship with them. And this covers just the buried cables here, the soil thermal resistivity for CS. CD is the depth of burial. I see a lot of posts on social media about, you know, what is the depth? What is the depth? In the main context of BS 7671, the depth is sufficient to avoid danger. There is a depth mentioned in horticultural agriculture where it talks about a depth for cultivated ground and a depth for normal. There is a depth mentioned in caravan parks, but otherwise it's just to avoid danger. Now, the building regulations, however, does give more visual guidance, but that's not part of the that's not part of the wiring regulations. So, we technically, from the wiring regulations perspective, sufficient to avoid danger. We've talked about the 3036 fuse, long disconnection times due to it operating only as a melting point. Yeah, still a good device to use. Can use it. It's just it creates a lot of handicaps to our circuit design. 524 cross-sectional area of conductors. It's a simple table. There is mention of neutral conductors actually before we look at this table. Let's look at 524. We have neutrals. The neutral conductor, if any, shall have a cross-sectional area not less than that of the line in single-phase 2-wire circuits and in polyphase and single-phase 3-wire circuits where the size of the line is less than or equal to 16 mil for copper or 25 for aluminium, or where it's required to 523.6.3. This is a good one. 524.2.2. The total harmonic content due to tripling harmonics. That's the third harmonic, which we touched on previously. If it's more than 33% of the fundamental line, so that's the first frequency. So you've got your first frequency. I'm trying to look at my reflection here. So your first AC wave, and then obviously there in that one wave, the third harmonic, there are 3 of them. And if their cumulative value of voltage is more than 33% of the voltage in the fundamental, yeah, then we'll need to increase the size of the cable accordingly. This one, for polyphase circuits where each line conductor has a cross-sectional area greater than 16 mil, or for copper 25 aluminium, the neutral is permitted to have a smaller cross-sectional area than that of the line, provided that the expected maximum current, including harmonics, if any, in the neutral conductor during normal service is not greater than the current carrying capacity of the reduced cross-sectional area. So you've obviously studied the harmonics, you've studied for the potential of a, you know, some harmonic content. If you've got non-linear loads, this is most likely not going to be achievable. Or the neutral conductor is protected against overcurrents. We mentioned that back in chapter 43, but we did say that it will not be an independent device. It will be protecting against overcurrent, but it must disconnect the low conductors as well. Or the size of the neutral is at least 16 mil or 25 mil, depending if it's copper or aluminium. And then we have this table, minimum cross-sectional area of conductors, and it just tells us minimum size for light circuits, copper 1 mil, Aluminium 16mm. Now, whilst there is a resistivity difference here, this is mainly due to the material's mechanical strength. Aluminium is a much softer conductor, and so it's sized larger for mechanical strength. That's quite often the reason why aluminium is used. It's light and soft, but we need larger cables due to that strength. And if you had a light circuit wire in aluminium, you'd know that you'd be struggling to find accessories to connect 16mm into. That's just obvious. So you would see that more with some machinery and some high voltage stuff. And then just after that is the volt drop section 525. Now, it's a very important thing to understand. Volt drop is from the supply origin to the end of the final circuit. So when we do a design, let's say that this is my system. If this is my intake and this is my load, then remember, in between this there's the intake to the main consumer unit. There may then be a sub main to a local consumer unit, and then my final circuit. So the volt drop is total volt drop. Okay, we get the value of volt drop from the part in the cable selection chart that we saw earlier on, the millivolt per amp per meter, and we're going to use that in an example very, very soon. But we must verify the volt drop. Now, there is a table in Appendix 4, 4AB, which is just before the just after the reference method table, I think. Yeah. Actually, it's before it because it's 4AB, not 4A2. It's fine. Here we go. Page 383. So it's just after all those formulas. And that tells us the volt drop there. So the maximum allowance for volt drop for a public supply, so that's an imported supply connected to the national grid kind of thing. 3% lighting, 5% other use. So we're talking about 11.5% and 6.9%, because that's off 230. And then obviously, if you're on a private supply like a standard diesel-driven generator or something, or a PV or something, then we have lower maximums due to the small. It's just probably a lot smaller an actual network. So we need to do the volt drop calculation whenever we do a cable size selection. The last step is to verify the volt drop, and what we compare it to is these maximums. So 5%, 3%. But bearing that in mind, when we do things like a sub main, let's say there's another fuse board here. The cable feeding this must be of low volt drop to allow some leftover volt drop for the cable being connected to that board. So do always make sure that whilst we know the maximums, if we're doing a sub main, we go nowhere near the maximums, because if you actually go to the maximum on your sub main, you're then saying, right, all your final circuits aren't allowed any volt drop. So do sometimes be aware of that. Okay, we're getting to the point where we're going to have to start actually having a go at one of these. So to summarise, Appendix 4 details the current carrying capacities and volt drops for cables, flexible cords. It's got the formulas in it, and it's got the volt drops in it. It's got the rating factors in it. And this is what we're going to do. We're going to find IB, IN, then IT, and then rating factors. There is a sequence. I'm trying to. I wish I actually. I'll probably flip to a camera at this point to kind of just carry this part on. But we're going to do this, and then we're going to verify volts drop, and that'll do for the PowerPoint. I'll now switch to a pad and pen kind of thing to go through a example that I'll just make up as I go along. So we'll do that now. Okay, so the way to approach it is always the same, and let's remember the basics. So we must remember coordination. IB is less than or equal to IN. It's less than or equal to IZ. Let's remember that as a starting point. We also know that we need a circuit. So let's go with a piece of equipment such as a heater. Let's call this heater 10 kilowatts at 230 volts. Let's say that the protected device is a, I don't know, let's say the board's got a BSPN61009 type C RCBO. Okay, let's say that the cable has a run of 27 meters. Let's say that, okay, so equipment is this, power is this, voltage is this, protected device is this, length is this. We now need to consider the method of installation. So let's go with a let's go with a surface clipped. Alright, which we know to be reference method C for now. Rating factor stuff. Alright, ambient temperature. I don't know, 35 degrees. Grouping. 3 other circuits. All of similar loads, and that's important. No thermal. Insulation along the route, maybe, because I don't know. Alright, let's just round it out like that. And so what we're looking here is we've got a building with a roof, the first floor, and we're saying board's down here, and we've got a cable run going up with 3 others. So there's boom, 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 and then along here there's going to be a heater. Maybe there's a few heater circuits kind of thing like that. I don't know. And there's something else in the loft, whatever. But we're looking at this one in the middle here. So we're going to have grouping here of 4, and then maybe there's grouping here of 2 for that one, and then 1 carrying on. Right? And maybe the other cable stops here for this heater, and this one carries on to the loft. So grouping wise, the worst case scenario is this part, and it's 3 other. That's fine. The ambient temperature of 35 degrees exists here and here. Alright, which is important because we may have to combine these factors. Okay, so quickly, we've got a heater at 10 kilowatts at 230 volts, RCBO type C, surface clip, reference method C, 27 meter run. We have an ambient temperature of 35 degrees C, 3 other circuits in the method of, in the circuit, no thermal on the route, and that's just a quick layout just so you can see what I'm thinking. Board, 4 cables, there's R1 plus 3 others, and then it's installed there, and that's about 27 meters there. Great. Let's take that off. Put that there to remind us. So the first thing we need to do is IB equals. IB is equal to design current. Design current is power, 10 kilowatt, over voltage. So I'll get my calculator going. Not about 3. We're keeping it simple, so we're not going to do 3-phase or anything right now. I can do some more examples on this kind of thing if we decide that we need it. So power over voltage, 10,000 over 230, 43.478, so 44 amp. IB is equal to 44 amp. Power over voltage, P over V. Okay, now remember coordination. Our IN, which is the nominal rating of the protected device, must be greater or equal to IB. So the next protective device rating above 44, well, I actually know that you can get a 45 for some mags. You may only depending on your manufacturer, you may only be able to get 50. Depends on who you're using, really. Okay, but that's coordination. 44 design current, 45. Now, if this load was a load that maybe had starting currents or like an inductor, then maybe a 50 would be better, because this could trip maybe with switching operation. Remember, it is a Type C though, so we'll have a little bit of allowance. Being just a heater, I don't think there's much concern of that, but we may want a bigger gap between IB and IN sometimes. Alright, so the next thing to determine is, well, I need to get IZ, but to get that I need IT, and IT is equal to I, and this is the real question now. Let's go to Appendix 4. Which formula do we use? So Appendix 4 gives us these formulas. They start here, single circuits, and it gives us a formula here which we can call equation 1 for single circuits. Now you'll notice when you look at that formula, the only rating factor missing from that is CG, and CG is the grouping factor. Well, that's no surprise considering that's a single circuit formula. When we go to groups, the difference between that formula, equation 1, and this formula, equation 2, is simply CG's been introduced. So those two formulas are just one's minus a CG. So we're gonna go with this grouping formula, but here's the question, okay? If overload protection is not required, then instead of, you'll notice here we've gone with IN on the top line, IN on the top line. But if overload protection is not required, we actually could use IB on the top line. So will a heater overload? No, it won't. It's not a motor. It's not a socket outlet circuit. So I'm going to go with IB over, and I'm going to use this formula. Yeah, so equation 5. But I'm only going to use the rating factors that are there. So is there a CG factor? Yes, because there's grouping. Is there a CA factor? Yes, because we have an ambient temperature. Is there a CS factor? No, it's not outside. Is there a CD factor? No, it's not outside. Is there a CI factor? There's no thermal insulation. And there's not, in the duct in the ground, there's no CC. And because this is overload protection is not required, you'll notice that the CF factor is also missing, because we don't need it if overload protection is not needed. So actually this is all our formula looks like. So let's rewrite that. Equals IB, which is 44, over CGCA. Let's find CG then. CG is the grouping table. So we go to the tables, table 4C1, rating factors for grouping, and it was 3 other circuits clipped direct. So we go to the reference method C1, single layer on the wall. There are 4 because it's 3 others, so it's a 0.75 factor. 0.75 times CA factor, ambient temperature is 35 degrees. Something we've not actually said here is if the cable's thermoplastic or thermosetting. So let's just put it as thermosetting. plastic, 70 degree C. That's important because we need that here. We need that in our CA table, table 4B1. Our ambient temperature is 35 degrees. So 35 degrees, 70 degree thermoplastic, 0.94. The question of do we multiply these together? Well, yes, because they coexist. They don't happen one and then the other. They coexist here. So we multiply these together, which gives us, we can either work it out with brackets if you wanted to. Depends on how good you are with your calculator. But just in case you're not very good, that's the new factor there, 0.705. So you can see multiplying the two factors creates a new lower factor. So that's the new factor, 44 over 0.705. So 44 over 0.705. And what we're going to end up with is the 44 going up to a new value. And it's going to be 62.4. So we get IT is equal to 62.4. So let's call it 63 amp. Okay, now it's IT. This is a tabulated value. What we now need to do is go and select an IZ with that IT. So we need to go and get that. So we didn't actually say what type of cable it was. We said it's a multi-core. Let's call it a multi-core non-armored. So let's go to 4D2A. Oh, which is the one I just opened up on. That's great. Okay. Oh, get the regs book round. So table 4D2A multi-core 70 degree thermoplastic insulated in thermoplastic sheath cables, non-armored. Reference method was C. Single phase. Reference method was C. Clip direct, reference method C. Single phase circuit. We want the next number above 63. Oh, well, it's bang on 63, and that is 10 mil. Reference method C, single phase, 63 amp, 10 mil. So that's absolutely fine. So IZ equals 63 amp, which is a 10 mil cable. Okay, so just to conclude, IB, select IN, tabulate IT with rating factors, then select IZ. And we've got coordination. IB, IN, IZ, IB, IN, IZ goes up. That's coordination achieved. Sizing of the live conductor is then verified. What we haven't verified though is volt drop. Formula for volt drop. Volt drop is equal to the millivolt for every amp for every meter. Okay. If we look at the table 4D2A, there's a table on the next page of 4D2B. And in there we want 2-core single phase cable. So column 3. And we go down to our 10 mil. 4.4. So it equals 4.4 millivolts per amp. 44 per meter length, 27 over 1,000. The over 1,000 is to get us a volts value instead of a millivolts value. Times 27 over 1,000 equals 5.227. So let's call it 5.23 volts. Okay, so the maximum requirement, is this a lighting or a power circuit? It's a power circuit because it's a heater. So the requirement for that, maximum volt drop for public supply other is 11.5 volts. Okay, so it's 5%, and that's absolutely fine. So 5.23 is okay because 11.5 volts is achieved. All of this means that this scenario requires 10 mil line cables. Okay, and that's the process. So IB, IN, IZ. Start off with that. Power over voltage. To get IB, select your IN, which you're given in the scenario. IZ, you have to calculate. You have to obtain from the book, but you need IT first. And to get IT, you use the formula in Appendix 4, which requires selection of rating factors, which are given to you in the scenario. All right. I'll add some examples of this. Probably as a resource, but what I'd like to do is maybe a stream or two where you guys can feed to me scenarios. You can tell me the equipment, the length, the ambient, just so that this doesn't look like it's rehearsed. This needs, you need to practice this, and retention is the best way to take this in. It's when you're able to do this kind of quick, very quick cable calculation that you realise how useful the regulations are and how easy it is. Something we haven't verified yet is the effectiveness of a protective conductor within this cable. We'll do that in chapter 54 later on. So in chapter 54 later on, I will refer us back to probably this exact scenario. So something I will need for then, which we haven't decided yet, will be the earthing arrangement, which we'll call right now a TNS, because why not? Alright, so we'll work it out later on, but let's just work with that for now. So we've covered in this video, we've talked about the sizing of the conductors, and we've gone a lot into Appendix 4. Just familiarise yourself with the Appendix 4. Okay, end. I'll see you in the next one.